Hello everyone. In this lecture, we will continue the study of generation of permutations and also discuss generation of combinations. So first, we introduce a new concept called inversion of permutations. Here's a definition. So for a permutation, A1, A2, all the way to AN, 1, 2, 3, all the way to N, an inversion of this permutation is an ordered pair AK, AL, such that KL is between 1 and N, and also K is less than L. And moreover, AK greater than AL. The reason we call it inversion is that for the index, K is less than L, but for the value corresponding to K and L, you have different inequality. You have different sign. So for example, if we have the following permutation of 5 elements, then we can enumerate all the inversions as follows. Here. You have 4, 1. For 4, you have 4, 1, 4, 3, 4, 2. There are inversions. And then for 5, now let's look at 5. For 5, you have all the possibilities. 5, 1, 5, 3, 5, 2. And then for 1, you don't have any. And for 3, you have 2. So you have 3. Let me write here. 3, 2. So total number of inversions is 1, 2, 3, 4, 5, 6, 7. Is 7. So in some sense, the total number of inversions measures how far this permutation different from differs from the identity permutation 1, 2, 3, 4, 5. Okay, then it's a natural question to ask, what is minimal possibility, the minimal inversion number, and what is the maximal inversion number? So minimally, you can have 0 inversion in total. That corresponds to the identity permutation. And the maximally, you can check for a permutation of n elements. At most, you can have n choose 2 inversions. That corresponds to permutation n minus 1 and all the way to 1. You can prove this, and I leave it to you. Okay. So next, we are going to discuss some final description. So if we only care about the number of inversions, you may have different inversions different permutations correspond to same number of inversions. But so you may guess the inversion is less accurate than the permutations. But in fact, we have the following property. First, you can ask the following question. If you brave enough, can we recover the permutations from the information of inversions? Okay, so the answer is yes, but before we give the explicit description, we introduce the following notation. So for a permutation, I1, I2 all the way to IN. So it's a permutation of n elements. Let Aj be the number of inversions whose second component is J. There's another description, that is Aj, IE means that is. Aj is defined to be the total number of integers that precede J in the permutation but are greater than J. And for different J, you can define different Aj, and the sequence. Then you have a sequence. The sequence A1, A2, all the way to AN is called the inversion sequence of the permutation I1, I2, IN. And it's easy to see the summation of all the AI, just the total number of inversions. Okay, so let's look back to the previous example, 4, 5, 1, 3, 2. So what is A1? So A1 is a number of integers precede J. So since you have 4, 5 precede J, precede 1 and 4, 5 greater than 1. So this is 2. And for A2, similarly, you have 4, 5, 3 before 1 and before 2, and 4, 5, 3 greater than 2 strictly. So this is 3. And then A3, you have 4, 5. And so this is 2. And A4 is 0. A5 is also 0. And you can check the total number, the summation. Is 7, just the total number of pairs. total number of inversions. Okay, and then we make 2 remarks. So first, it's easy to check that a1 is an integer between 0 and n minus 1, and a2 is an integer between 0 and n minus 2. And for an minus 1, it's between 0 and 1. The last one, an, is always 0. And secondly, we can look at the following sequence of integers. So how many b1, b2, bn integer sequence such that 0 is between, b1 is between 0 and n minus 1, b2 is between 0 and n minus 2, bn is between 0 and 1, bn minus 1 is between 0 and 1, bn is 0. And it's clear that you have n choice, notice that here you start with 0, therefore you have n choice for b1, n minus 1 choices for b2, and 2, 1. So totally you have n factorial sequences b1, b2, all the way to bn. Okay, and then noted that. So that's a usual way we do research. When you have some coincidence, don't just oversee it, and you should have the courage to do some brave guess. So here you noted that n factorial equals n factorial. So this n factorial is the total number of B sequences, and this is the total number of permutations. Okay, then if you brave enough, you can guess. Is it true that permutations of 1, 2, 3, 4 all the way to m is bijective or has a bijection to the inversion? Sorry. Yeah, you can see inversions b1, bn, or okay, let's see this. To b1, bn sequences such that the above inequality holds. Okay, and the correspondence actually, if you go this way, we expect this is just an inversion sequence. For a permutation, you take its inversion sequence, you get B. And now the question is, can we do the inverse construction? That means you are given some B sequences. You are given a B sequence. Can you construct a permutation with a prescribed B sequence? So that's the usual kind of a little bit more complicated direction. You need to do some construction. Okay, and so the idea, I mean, the reason why we care about this is kind of like something in the cipher, as a cipher or cryptography. Just like if you have 3 persons, 2 of you are friends, the other one is an enemy, and if two friends want to communicate something without letting the third person know, probably if they have the accurate information permutations, if you tell directly, the third person may hear. So they transform it to B sequences. And if the third person don't know they are talking about the inversion sequences, then even he knows the B sequences, he cannot recover the permutations. So that's the usual way, the usual idea for the common cryptography. Probably nowadays they have some more advanced idea, but for the classical code, usually they do it in this way. Okay, to construct, we give two algorithms. So for the first algorithm, we will call it a relative method. This is because until the last step, you can know what the exact position each number sitting in. For the next one, the absolute method, each step you figure out the value in some position. Okay, so for step n, you write down n. For step n-1, we consider the item be n-1 in the B sequence. Notice that by the assumption, Bn-1 has two choices, 0 or 1. So if this is 0, then n-1 must be placed before n. Otherwise, let's write, if Bn-1 equals 1, then n-1 must be placed after n. And similarly, for the n-k step, consider the item Bn-k, and by assumption, you have k plus 1 choices. And notice that in steps n-1 all the way to n-k plus 1, we already put the k numbers n-1 all the way to n-k plus 1. Numbers. So have been placed in the required order. And then if Bn-k is 0, then n-k must be placed before all the numbers from previous step n-k plus 1. And if Bn-k is 1, then n-k must be placed between the first two. Numbers. And keep on going. So lastly, if Bn-k just k, then n-k must be placed after all the numbers. We will give an example later. And the last step, you can do the same thing for 1. Okay. And this is a relative method because, for example, in the first step, you write down m. and we just know the relative positions for a certain number in the intermediate steps. So even in the last step, the step before the last step, you don't know what is the accurate position, for example, for 2. Okay, you just know some relative position. And if you prefer know the relative position to know the absolute position in the intermediate steps, we have the following method, following algorithm. We begin with an empty locations. 1, 2, 3, all the way to n. And the first step, put 1 in location numbered b1 plus 1. And in step 2, continuing from the left, put 2 in the b2 plus 1st empty location. Okay, so here the important thing is, anyhow, you need to have some relative flavor in some place. Essentially, they should be equivalent. So here, when we count the locations, we always count the empty locations. For example, if 1 is the position for 1 is before b2 plus 1, then you need to add 1 more position. So you should put 2 in b2 plus 2. Okay. And keep on going in the case step. So, oh, sorry. Here's counting. So counting from the left, put k in the bk plus 1st empty location. And for n, because bn is 0, so you just put n in the last empty location. Okay, now let's run the algorithm once. So suppose you have 1, 2, 3, 4, 5 elements, and the B sequence is 3, 3, 1, 1, 0. So this is B1, B2, B3, B4, B5. And if we run algorithm 1, so you do last step first. So you put 5 here, and then you look at B4. Since B4 is 1, so you should put 4 behind 5. And then for 3, you should, because B3 is 1, you should put 3 in between the first 2 numbers in step 4. So 5, 3, 4. And for 2, because it's 3, so you should put between after all 3 numbers. And the last step, you should put 1 in between 4 and 2. So this is algorithm 1. Okay, and then for algorithm 2, we first fix 5 positions. And we start with the first item in the B sequence is 3. So you should put 1 in the 4th, 3 plus 1 in the 4th position. So it's here. And in second step, it's also 4. So you need to count the 4th empty location. So 1, 2, 3, 4. So 2 should be here. And then you have 1. So you should put 3 in the second position. You have 1 again. Then need to count the second empty position. 4 should be here. And 5 occupies the remaining position. And then you noted that they give you the same answer. They should give you the same answer. Okay, next, I just want to recall you that although we didn't mention that before, but in linear algebra, we already know this and use this a lot, use inversions a lot. Linear algebra. So for example, if you have a matrix, a square matrix Aij, I is from 1 to n, j is from 1 to n, and then we can talk about determinant of the square matrix A. You can write as epsilon I1 to In, A1 I1 times A2 I2 times all the way to AN IN. And here, I1 IN runs through all permutations of an element or a set of n elements. Okay, so here epsilon is called a signature. It's always positive 1 or negative 1. And the rule to determine that is that it's 1 if total number, in the language of inversions, if total number of inversions is even, it's negative 1 if the total number of inversions is odd. Okay, so I leave it to you. Verify it for 3 by 3 matrix. At least do it once for 2 by 2. Okay, another another common notion is that when epsilon I1 to In equals 1, or the total number of inversions is even, we call I1 In an even permutation. And when it's negative 1, or the total number of inversions is odd, we call it odd permutation. This is quite important later on if you study exterior algebra or tensor algebra kind of stuff. Because in that case, when you exchange two elements, they contribute a negative sign. So if you are studying or majoring in computer science or want to learn more discrete stuff, linear algebra, I think it's more important than the calculus. But of course, if you are good at both, it will be better. Okay, next we turn to another topic, another similar topic, that is generate combinations. And the question is how to list all subsets of A's, or how to use computer to enumerate all the subsets of S. So list all subsets of S. The reason why we want to list or enumerate all the subsets of S, or all elements of some set, is because sometimes you need to test some statement for each element. So at each step, actually, at least you need to know what element you have. So that's why people care about how to generate permutations instead of generate the permutation in an effective way instead of just knowing some method exists. Okay, now first let's look at one example. When n is 3, and we denote the 3 elements as 1, 2, 3. So how to generate all the subsets? We do the following way. So on the left, we list let's list this subset, and on the right side, let's use 1 and 0 to denote if the corresponding element is in the subset. So in the subset, we use 1, 0. Means not in the subset. Okay, so for empty set, we have 0, 0, 0. And then for one, you have 0, 0, 1. For 2, you have 0, 1, 2. For 1, 2, you have 0, 1, 1. For 3, you have 1, 0, 0. And then for 3, 1, or 1, 3, you have 0, 1, 1. 1, 0, 1. 3, 2. 1, 1, 0. 1, 2, 3. You have 1, 1, 1. Okay, then totally, now, totally we have 2 cubic 8 subsets. And here you already enumerated them. If you look at the right side more carefully, then you will see that's just base 2 numerals, or 2 digits. So if you view this as a 2-digit number, the 0, 0, 2. So when you turn into 10-digit number, that will be 0. And this is 0, 0, 1 in 2 digits. This is 1. Similarly, this is 2, 0, 1, 0, 2, 3, 4, 5, 6, 7. Okay, and then it's easy to see that all subsets set consisting of n elements. has a one-to-one bijection to two base digits. Here you have n positions, 2, and all the way to 1, 1, 1 is also n positions, 2. Or if this is 0, this is 2 to n's power minus 1. Okay, then we have the following algorithm for generating the subsets of xm minus 1, xm minus 2, x1, x0. Notice that here we use some different notation. Sometimes we starting from 1, sometimes we start from 0. That depends on we are doing the mathematical reasoning or the algorithm. Because for the computer, usually when you see natural number, it starts from 0. The built-in number starting from 0. Okay, and by the previous remark, we know that so actually a subset is associated with a 0, 1 sequence, am minus 1, am minus 2, a1, a0. So we only need to enumerate all such sequences. The algorithm begins with the A sequence 0, 0, 0. And if it's not the last one, then by that I mean it's not 1, 1, 1. Do the following. So find the smallest integer j. Of course, j should be between 0 and n minus 1, such that aj is 0. Secondly, replace aj with 1 and replace each of aj minus 1, aj minus 2 to a0 with 0. Since such j is smallest than aj minus 1 to a0 originally are 1. So actually this is just by adding 1. Okay, and this is so-called lexicographic ordering of n tuples. The algorithm is pretty easy, but we have some drawbacks. Drawbacks. So first drawback, the immediate successor may differ a lot from the subset before it. Just like if you think about if you have 0, 1, 1, 1, 1, 1, then the next one will be 1, 0, 0, 0, 0, 0. Okay, so they differ in all elements. This is not so satisfactory because when you do do searching or whatever, you want the data close to each other in some natural way. So our question is, can we generate the subsets of a set in a way such that the immediate successor differs as little as possible. And so what does as little as possible mean? The most we can expect is include one element or delete one element. That's the most we can expect. Okay, probably this is not so restrictive. Next, we give a geometric description, which will be kind of more nature question related the requirement for the algorithm to the geometric picture. So first, if you have one element, then you have two subsets. Let's denote 1, 0. Okay, we connect them because they differ only by one element. So you can also view this is a unit interval in the x-axis. And next, for n equals 2, you expect 4 subsets. You can visualize it in the xy plane as a unit square with a coordinates 0, 0, 1, 0, 0, 1, 1, 1. Let's omit the parentheses for convenience. Okay, and then in the in dimension 3, you can do the same thing in the XYZ space. This is 0, 0, 0, this is 1, 0, 0, 1, 1, 0, 0, 1, 0, and 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1. Okay, and we connect an edge because these two vertices are different by adding or deleting one element. Okay, so here for Rn we cannot draw it on the paper because we never see any Euclidean space with dimension greater than 3 strictly. But at least you can imagine that each vertices has coordinates represented by a 0, 1 sequence, and the edges corresponding to subsets differs minimally. So minimally, just means including or adding one element. Okay, then what is the question? So question now is transformed into the following geometrical one. Can we draw a root along the edges that begins at some vertex and visited every other vertex exactly once. Actually, this when we learn Hamilton cycle, you will know this is very similar to Hamilton cycle or Hamilton graph. And actually here, if you look at the following algorithm we are going to introduce, you will see actually this is a Hamilton cycle. That means, so the remark is the following algorithm actually gives a root, not a root, gives a loop, closed loop, satisfying the above condition. That means visit every vertex exactly once. Sorry, visits. Okay. Next. Since we mentioned the Hamilton cycle, we should make a remark that not all the graphs have Hamilton cycle. For example, if you have the star shape, you don't have Hamilton cycle at all. So actually, this would be a very nice example of some Hamilton cycle. And in mathematics, I don't know too much about computer science, but in mathematics, those interesting models or the important series usually presents or exhibits different structures at the same place, just like Euclidean space. First, it's a point. It consists of points. Secondly, it's a linear space. You have linear structure on it. Thirdly, it's a metric space. You can define metrics. You can do measuring. Okay, so you have three structures on it. So that would be a good model. And some other nice theorems usually cooperate different structure in the same thing. And probably most people will not agree with me, but from my own opinion, I think all theories are based on the nice models. We understand the world from nice models and do some generalization and do some perturbation, just so you can recognize one book is different from two books. Why? Because in your mind, you already have the model 1, 2, 3, 4, 5, 6, 7, the natural numbers or the positive integers. So that's the model you're always comparing your object to. Okay, and now let's look at the proof. Whenever you have a difficult problem, let's look at the lower rank case. If you had two subsets, then you can start with 0 and then go to 1. And now a little bit complicated case is how to do n equals 2 case. So here is the algorithm. So step 1, you decompose this as 2 copies. So you have 2 copies. That means above you have 0, 1, 1, 1, and below you have 0, 0, 1, 0. So let's make 2 copies of 0, 1. And now you need to put in arrows. And step 2, draw arrows I should say in this way. Copy arrows for the below one, for the one below, and reverse it in the above. That means for the underneath one, you just keep it, or you just copy it from the previous case. And for the above one, you flip it, go this way. Okay, then we still need to connect them. So the rule to connecting these two pieces is that connect the end with the beginning. You can either, so here ends, you can treat it as the end of the above one or the below one, doesn't matter, because later on you see you actually have a loop. Okay, so in this case, actually we have, you can connecting these. Okay. Let's do one step further. Look at n equals 3 case. Now I'm sure it will be very well understood. So if you run the program once again, so first you make 2 copies, and for the below one, you just copy the arrows as well. And for the above one, you reverse the arrows. Okay, and the last step, you connecting the end to the starting point. Then you're done. So this is called reflecting or reflected gray code of order n. So that's a geometric understanding. And if you want your computer to run the actual program, then we can formulate in the following way. as follows. So first, the reflected gray code of order 1 is 0, 1. So first you have 0, and then the computer returns 1. Okay, next, suppose n is greater than 1 and the reflected gray code of order n minus 1 has been constructed. Okay, that will be, let's note as A1, 1 to all the way n minus 1, 1. This is the first subset we have. And then you have A1, 2 all the way to an minus 1, 2. The superscript 2 means this is second returns. Okay, since totally you have 2n minus 1 subsets, so the last one will be this 2n minus 1 and minus 1. Okay, so why we call it reflecting? Because when we construct the n's, let's change the notation a little bit. So to construct the order n, you first put a 0 in front of all this code, and then you do reflecting along the green mirror, so which gives you 2a n minus 1 to n minus 1, a1 to n minus 1, and then a n minus 1 to n minus 1 minus 1, a1 to n minus 1 minus 1, and a n minus 1 2, a1 2, a n minus 1 1, a1 1. Okay, then you put 1 in front of that. So that's exactly the geometric meaning. So the mathematical meaning for our geometrical description. And a remark, a very important remark is, it is cyclic. You will see A1, an minus 1, 1, a1, 1. Next should be a0, an minus 1, 1, a1, 1. So they are adjacent. So if you look at the picture, what does that mean? That means although we didn't draw it, but actually you do have a closed loop. So for example here, and then here. So so this is connecting the beginning to the end. Sorry. let me write in a more precise way. Connect the end of the below to the beginning of the above. And now if you connect the end of the above to the beginning of the below, then you have a closed loop in total. So that will be a Hamilton cycle. So very important remark. It is a good example of Hamilton cycle. Now, if you want put it into computer, we do some variation. Because if we use this reflecting method directly, then you need to restore a large portion of data. That's not so convenient. So we develop a little bit different way to generating the gray codes. So the result is still gray code, but you use some variation to simplify the computation. In the reflected gray code or the n. So begin with 0, 0, 0. And while it's not the last one, actually you can see the last one will be 1, 0, 0, 0. Do the following. So first, compute sigma. So this is a numerical invariant for each A sequence. This is a summation of all the numbers, of all the items. And then if the answer is even, we change A0. That means 0, 1, 1, 0. 0 to 1, 1 to 0. And otherwise, else, find J such that AJ is 1 and all the items on the left is 0. Or in other words, the first one from the right, and then change AJ plus 1. Still use according to the rule that 0 to 1, 1 to 0. Okay, I will not give the proof here. I think the idea is more important. And if you have a geometric understanding of the gray codes by picture, I think more or less is enough. But of course, if you want to know more, please read the textbook. It gives you an explicit proof. Okay, I will stop here. Next time we will continue to finish the generation of the subset, and then we turn to a little bit slightly mathematical flavored material called partial order and equivalence relations. Okay, thank you. I will stop here.